Hello everyone, we want to do another example, and in this example we have a 20 cubic feet rigid tank initially have a saturated R134A vapor at 160 psi, and as a result of heat transfer from the refrigerant the pressure drops to 50 psi. We need to show the process on the PNU diagram with respect to saturation lines and determine the final temperature, amount of refrigerant that has condensed, and the heat transfer from this process. Okay, so this is basically a problem related to the second law of thermodynamics and first law of thermodynamics. And again, you have to basically understand what the problem is. So it's a rigid tank, right? So what do you get from the rigid tanks is that your volume does not really change. Your volume stays the same, so V1 is equal to V2. That's what you get from this problem. And initial pressure what we have is 160 psi. P2 is 50 psi. And remember here, if you look at here, it says saturated R134 vapor, right? So the initial state of the system is saturated vapor phase, right? So this is initially saturated vapor, which we can get it from we can get more information about this state from the saturated vapor liquid mixture tables, right? And then the pressure drops, right, and to 50 psi. All right. So another constant volume process. So if you want to plot the PNU diagram for this process, let's assume that this is our PNU diagram. Inside the envelope is the two-phase liquid-gas mixture. Critical point, bubble point, dew point line, bubble point line. Compressed liquid area, superheated vapor area, right? Okay, so then initially it's saturated vapor. It means it's at some point on this dew point line. So let's assume that it's here, and the pressure at this point is equal to 160 psi, right? And then your pressure drops at a constant specific volume. Why? Because it's a rigid tank and the volume does not change. So and it's a closed system, right? And therefore your specific volume does not change. So state 1, state 2, right? Okay, so at state 1, pressure is 160 psi, saturated vapor. How to get the information from this state? Before getting the information, let me write the first law of thermodynamics so we know what we're doing actually here. So if you write the first law of thermodynamics, delta E, E2 minus E1 or E in minus E out, it's equal to delta E system, right? And in this case, since there is no work being done on the system, so work is 0, right? Let me write this here. Work done. And then you have the heat transfer, which your system loses heat because it becomes two-phase, right? So there are some heat transfer, but your system lose some heat. So remember the equation was W in minus W out, Q in minus Q out, and then the whole thing was equal to change in potential energy, kinetic energy, and potential energy, and then delta U, right? Okay, so based on that, we don't have any work being done, or the system does not do any work, so this term is 0. There is no heat coming in. The heat is leaving our system because we're going into the two-phase. So this is 0, so we have minus Q out, right? And then no potential energy change, no kinetic energy change, potential kinetic, and these two are 0, and the only thing that remains is delta U, which you can write it in terms of the specific internal energy, so U2 minus U1, right? So that is our equation, which you can remove this negative and write just Q out is equal to M, then U1 minus U2, right? So that's the same equation. All right, so this is our first law of thermodynamics, and one of the properties that we want to find is the heat transfer, which is Q out, right? So in order to find that, you need to have U1 and U2 and state of the system at the point 2, right? At the state 2. So P1 is P1 is equal to 160. We mentioned that, right? PSI. System is in saturated vapor phase. Which table do you use? You have to go to table. Since this is a saturated vapor liquid mixture, then table A11, but this is an English unit, so that's English A11E. So I have to go all the way down until I get to table A11E. Since I know the pressure, that's what I need to look for. Just a second. So I'm in the English tables, English unit tables, A4, A5, A6, A7, 8, 11. All right, cool. So I'm here finally, and I need to go to 160 psi because that's my unit. And actually, probably I should use A12, right? Because that's the pressure table. Yeah, I should use A12B. All right, so 160 psi, and it's a saturated vapor mixture, so our temperature is actually 109 degree Fahrenheit initially, and the specific volume of our system, we need to read it from nu G, that's 0.27 and 0.29 actually, and I need to read the internal energy, which is 108.51, right? Okay, so I'm going to go back here and I'm going to write the information. So nu1 is equal to nu G, and that is equal to 0.29 339 cubic feet per pound mass, and U1 is equal to UG 160 psi, right? And that is equal to 108.51 BTU per pound mass. So that's the initial state of my system. And next, what I'm going to do is to find the phase state 2, right? So state 2, my pressure is 50 psi, and I am definitely in two phase. And what I know from this state is not just the pressure, but it's also the specific volume, because it's a rigid tank, so the specific volume stays the same. So my specific volume at the state 2 is also equal to 0.29339 cubic feet per pound mass. And then with these two information, I need to go to the two-phase tables again, and my pressure is 50 psi. So that's my pressure, right? And my temperature is dropping, of course, to 40.23. That's my temperature, and that's actually what you need to find for the part A, right? So my pressure is 50 now. I'm in two phase. The temperature at that phase, at that state, is 40.23. So let me write down that number. So T2, that which is part A of this problem, is equal to 40.23 degree Fahrenheit. I can get some more information from this point. I need the internal energy. I need the some other properties. So I would need to calculate that. I will tell you in the next part. But you can read your nu F, nu G, UF, UFG, and UG from this table as well, right? So all right, so I can write those information for you. So nu F is 0.01252, and nu G is equal to 0.94909, both of them cubic feet per pound mass. From the table, UF is equal to 24.824, and also UFG, which is the difference between the internal energies of gas and vapor and liquid, is 75.228 BTU per pound mass, right? All right, cool. So what do we need to do in order to find where we are here? So we know some information about the specific volume. This is our new F2, and this is our new G2. We read this data from the table. However, and I should mention this is 50 psi, right? However, I don't know where exactly my point is, right? So remember the equations, we defined the quality. So for the quality, we could use quality to find the internal energy, specific volume, all the properties in the two-phase envelope area, right? In order to calculate the quality, I need to calculate the mass of the system initially. So the mass, I can calculate that because quality is a mass ratio. So mass is V1 over specific volume 1. That's 20 divided by 0.29339. You can put the units, 68.17 pound mass. So I can calculate my quality at 0.2 by knowing the specific volume, which is 2. I guess let me write the equation first. This is nu 2 minus nu f divided by nu fg, right? And that is 0.29339 minus 0.01252 divided by nu fg, which is the difference between the specific volumes of vapor and liquid, minus 0.01252. That is almost 0.3, right? So that's our quality. And then if you have the quality, you can calculate the mass of the liquid in your system, which is 1 minus x2 multiplied by total mass. That's 1 minus 0.3 multiplied by total mass, which we did calculate that, 68.17 pound mass. That is 47.73, right? And that's the mass of the liquid at that state. And you can calculate the internal energy, therefore, which is UF plus X2 UFG. That's not new, that's U. FG, which is 24.824 plus 0.3 multiplied by 75.228. You put the numbers in, you get 47.38 BTU per pound mass. All right, finally, you want to calculate so this was part B, right? The amount of refrigerant that has condensed. So this, I forgot to write this, pound mass. This is the amount of refrigerant that has condensed into the liquid. That's MF, right? How much of the total mass is liquid. And finally, I want to calculate the heat, which I'm going to use this U2 that I just calculated, right? So Q out is equal to MU1 minus U2 from the first law of thermodynamics, 68.17 total mass. 108.51 I read from the table at 160 psi minus 47.38. I just calculated here, and that would be 4167 BTU of heat being lost from this process. All right, that's it for this problem.